Hi, my name is Ilan Levine. I am a professor of physics and astronomy at Indiana University, South Bend. My area of research is in the experimental search for particles of dark matter and the properties of neutrino. In this first lecture, I'm going to talk about the evidence that we have that the vast amount of the mass in the universe is formed from an exotic material that's not atoms and has some very strange properties. In the second lecture, I'll talk about how my colleagues and I are attempting to detect these elusive particles. So let me start with a bold claim. Almost all of the universe is inherently invisible. It's not just unseen, it's that it can't be seen. It doesn't interact with light. So let's start with the easy stuff. The slice in red here is the portion of the energy density of the universe attributable to atoms. So all things that we see around us, our neighborhood, the clouds, stars, galaxies, etc., anything made from atoms is this 4% of the energy density of the universe. Note that that corresponds to about 15% of the mass of the universe. About 1/5 of the energy density of the universe is this material that we're talking about today called dark matter. This constitutes 85% of the mass of the universe. And this 3/4 of the universe shown in green here is something I won't be going into today. It's an interesting topic in its own right, called the dark energy. It's different from dark matter, although the two names sound similar. This substance, whatever it is responsible for the fact that the universe is getting bigger and bigger at a faster and faster rate as time goes on. And it is a usefully humbling note that scientists didn't even anticipate the existence of this part of the universe that we now know exists until 1998. Likewise, the dark matter that we're talking about today only came onto our radar in 1930. Okay, so let's first talk a little bit about Newton's laws of motion and universal gravitation, which lies behind our story today. You know that if you let go of an apple, it's going to fall to the ground. And likewise, if you have a big rock at the top of a hill and push it, it will roll down the hill due to gravity. You probably also have heard that the moon orbits the Earth because of the gravitational attraction between the moon and the Earth. And Newton developed a set of laws of gravitation and motion that dominated science for hundreds of years. The force, say, between the Earth and the Sun can be written in this way, where the force here is F. G is a constant of nature called the universal gravitational constant. This might be the mass of the Earth orbiting the Sun. This would be the mass of the Sun. And R here represents the average distance between the Earth and the Sun, shown here. And one can use these equations to set up other expressions. So, for example, the velocity of the Earth depends on the mass of the Sun and the distance between the Earth and the Sun, and it can be written in this way. In other words, the farther we get from the Sun, the slower the velocity of the Earth orbiting around it should be. And the bigger the mass of the Sun, the bigger the velocity of the Earth around the Sun should be. And we can even invert that expression to solve for the mass of the Sun. So the mass of the Sun depends on the velocity of the Earth and the distance between the Earth and the Sun in this way. And so from knowing the Earth-Sun distance and the length of the year, which gives us the velocity of the Earth, we can calculate what the mass of the Sun must be. And this is a theme that we're going to be coming back to many times. For example, in spiral galaxies, if we look at a cloud of gas orbiting a spiral galaxy, the mass of the galaxy inside the orbit of that cloud will be equal to the velocity of the, oh golly, sorry about this, will be equal to the velocity of the cloud squared times the distance between the cloud and the center of the galaxy and divided by the gravitational constant. In other words, from measured orbital speeds of material around the spiral galaxy, we can calculate how much mass is inside its orbit. We can also relate the mass in the form of atoms of these astronomical systems to how much light is coming from them. So, for example, if we know the luminosity of a main sequence star, we can calculate what the mass of that main sequence star is. Likewise, for galaxies as a whole, if we measure the light coming from them, we know how many atoms are in them. And even for galaxy clusters, which are bound systems of galaxies held together by their own gravity, based on the amount of light coming from them, we can tell how many atoms are inside that galaxy cluster. Now, in 1930, Fritz Zwicky was studying the Coma cluster of galaxies, which has thousands of galaxies in it. And he measured the amount of light coming from these galaxies and was able to calculate then the mass in the form of atoms that made that light. But he also measured the speeds of the galaxies in the cluster, and he calculated the amount of mass necessary to hold that cluster together. And the problem is that he came out with different results. In fact, the total amount of mass from the speeds measurements said that there was 10 times more mass than the light method indicated. Zwicky said that this was evidence that a vast amount of dark matter was there, contributing mass, but not light. This wasn't widely accepted since many of the techniques to understand these astronomical systems and even the measuring equipment were still in their youth at that time. But in 1970, Vera Rubin and Kent Ford, with more modern equipment, were able to study the dynamics of spiral galaxies. And they looked at how fast things were moving around spiral galaxies as a function of how far they were away from the center of the galaxy. So in other words, it's this expression we developed before, or the expression written here. So what did they find? This is a plot of speeds that they measured versus the distance of the object whose speed they were measuring was from the center. And the data they have is the points with error bars here, the circles with little bars on them. Those are measure the amount of uncertainty in their measurements. Now, what was expected from Newton's theory of gravitation and laws of motion, assuming that what we see is all there is, was that the velocity distribution should look something like this. But what was actually observed is something fairly flat. So there's two problems here. The velocities they measured were way too big, and the speeds don't drop as 1 over the square root of the distance as they're supposed to. That could be explained by having a vast amount of matter in here that we don't see. This is the first piece of evidence that really made much of the community stand up and take notice that the dark matter problem was a real one. Since then, there have been many different kinds of measurements that indicate the presence of dark matter. So, for example, Einstein's theory of general relativity tells us that near any massive object, the space is going to be distorted, warped by the presence of mass. And light traveling near that warped space-time will be deflected in its motion. And so if we look at, say, what it might look like with this, we have this drawing here. We have this large mass creating a warping of space-time, and some of the light which was going this way from the object would get redirected to our telescopes. So to us, it would look like the object was over here, and some of the light might go this way and get directed by the curved space-time to our telescopes here from this direction. And so we would have another image of the same object over here. And in fact, with a perfect arrangement, you'd get a complete circle of images. What's shown in this photograph here, these golden objects are galaxies in a galaxy cluster, which are acting as a gravitational source of warping of space-time. And you can also see this faint streaky set of images. These are multiple images of the same distant background object. We know it's the same based on the Doppler shift of their light. And so again, we have two methods for measuring the mass of this galaxy cluster. We can measure the mass by the light coming from the galaxy cluster, but also we measure the mass by the amount of warping of space-time that results in these streaky images. And again, we find the total amount of mass determined by the gravitational lensing data to tell us there's 10 times more mass than there is in the form of atoms. We also have evidence from the early universe. This is a photograph of the universe when it was less than 1 billion years old. And what we can see is that there were already galaxies. If all the matter in the universe were ordinary matter, the universe would be too hot for these condensed systems to have formed. And when we model the formation of structure over time of the universe, the only way to get the types of structures that we actually see with our telescopes are to assume a universe that's 15% ordinary matter, 85% dark matter. Likewise, when we look at a system where two galaxy clusters collided with each other, forming the so-called bullet cluster, we have a composite image here from 3 different telescopes. Using visible light, we see the galaxies in the 2 clusters here, having passed through the collision. The X-ray emitting gas was measured for the 2 clusters, was measured to be here, and most of the mass of the 2 clusters is indicated by here as measured by gravitational lensing effects. And the important point here is that although most of the atoms in these 2 clusters are in the pink gas, most of the mass has passed through and separated from most of the atoms. Therefore, most of the mass is not in the form of atoms. We even have information from the very early universe when the primordial materials were made during the Big Bang. In the first 3 minutes, we had formation of the very light nuclei, such as hydrogen, helium, lithium, deuterium, and the ratios of these different types of atoms in the early universe depends very tightly on the density of protons and neutrons that are in the universe. And what we actually measure for the relative abundances of these elements tells us that the total amount of mass in the form of atoms is only 15% the mass of the universe as a whole. Likewise, when we look at the cosmic microwave background radiation, which is coming to us from a time when the universe transformed from being opaque to transparent, when it cooled off enough that neutral atoms could form and the ambient photons started streaming freely and stretching out as the universe grew, we find that the lumpiness of the universe is too high for the universe to be dominated by atoms. This lumpiness tells us that much of the mass in the universe was moving slowly compared to the speed of light at about a billionth of a second after the Big Bang. So now we have to ask, what are the properties of dark matter, which I hope I've convinced you there's strong evidence for. Well, if it's evaded detection so far, it must be intrinsically invisible. It's all around us. In fact, thousands of particles are going through your body all the time. You don't feel it because this is so very weakly interacting with ordinary atoms. In fact, a single particle of this stuff can travel through thousands of light years of lead bricks without bouncing off of a single lead atom because they're so rarely interacting. And maybe this sounds really crazy, but there are other particles that we've measured to exist called neutrinos, which are, there's trillions of them going through us all the time from various sources, including from the Big Bang. And we don't feel them because they don't interact with our body. They just go right through. And yet, it's only because of these really ghost-like particles that condensed systems such as stars and galaxies and people exist. So let's next talk about how we construct hypotheses as to what the nature of the dark matter is. And these tend to fall into two general categories, so-called natural guesses and ad hoc guesses. So what's an example of a natural guess, or what is a natural guess? These are guesses that arise from us attempting to solve other problems in nature, which happen to provide candidates to serve as the dark matter. So, for example, the question about why gravity is so much weaker than the other forces in nature has led physicists to posit something called supersymmetry, which implies the existence of a large class of particles, some of which could have just the right characteristics to be dark matter particles. In fact, they posit the existence of weakly interacting massive particles, which could have been created about a billionth of a second after the Big Bang, and which would be stable to this day. But there's also ad hoc guesses. These are guesses just based on us wanting to think up ideas for what the dark matter could be that just doesn't violate any known laws. So, for example, one type of idea is that maybe in the very early universe, there was a process, who knows what process, which created small black holes that are throughout space. These black holes would have to be small enough that we wouldn't see them in some of the techniques that we've used to search for black holes. But they would also have to be large enough that they're not observed evaporating explosively today. So that's another example of a type of guess as to the nature of dark matter. This is the type of hypothesis that my colleagues and I are most focused on, but other scientists make other bets as to what's most likely. So we know dark matter exists. Where is it? It would be all around us, going through us all the time. Now, we feel sunlight on our face because photons actually get absorbed by our skin, and we sense the energy of those photons by, the warming that they do to our skin. But neutrinos and dark matter just goes right through us, so we just don't experience them. So that's not as weird as it may sound. So putting together what we've discussed in this first lecture, I hope I've convinced you that there is a vast amount of mass in the universe that is not in the form of atoms, that this material has some exotic properties like being invisible and very weakly interacting, No one has seen or made convincing observations of particles of this dark matter. And however, this stuff is all around us and unfelt because it interacts with us so weakly. And then the question is, well, what are the properties? Well, stay tuned for part 2, and we'll discuss that. Thanks for your attention. Bye.